Every time you open an app on your smartphone, start your car, or boot up your computer, you are relying on a hidden brain doing all the work. We call this brain a microchip, or an integrated circuit. These brains are made of billions of microscopic on and off switches, called transistors, all crammed onto a surface no bigger than a fingernail. To manage this impossible scale, engineers split the building process into two halves. First, there's the front end, where we build what is essentially a microscopic skyscraper. Then comes the back end, where we cut those skyscrapers out and wrap them in armor. Once you see how this two-part division works, the most complex objects ever built by humans suddenly start to make sense. The front end is where the circuit is actually built onto a slice of silicon. This happens inside fabs, or clean rooms, which are thousands of times cleaner than a hospital operating room. On this tiny scale, even a single speck of dust would be like a massive boulder crashing into our microscopic skyscraper. Our foundation starts as a razor-thin, perfectly polished slice of pure silicon crystal called a wafer. In a step called oxidation, we bake this wafer in a high-temperature furnace to grow a thin, protective layer on its surface, giving us a fresh canvas to build on. These extreme cleaning and prep steps ensure we have a flawless base before we try to build even a single switch. Now we start printing our blueprints. In a process called photolithography, we shine ultraviolet light through a stencil to project the microscopic patterns of our circuit directly onto the wafer. Next, we use chemical gases to etch or carve away the unwanted material. This leaves behind the exact physical pathways we just printed with light. Then, we bombard the silicon with high-speed atoms. This changes how those specific areas conduct electricity, turning the material itself into a component of the circuit. This is the moment where those billions of tiny on and off switches, the transistors, are actually born. By changing the silicon's properties this way, engineers can control exactly when the material lets electricity flow through and when it blocks it. From here, we keep stacking ultra-thin layers of conductors and insulators on top of each other, building up our skyscraper level by level. After every layer is added, we use a super precise polishing process to grind the surface perfectly flat. It's like sanding a floor until it's smooth enough for the next level to sit perfectly on top. Finally, we lay down tiny copper pathways to wire everything together. It's like a massive network of streets connecting every house in a city. By the end of this front-end stage, we have a completed wafer, a single disk containing a grid of thousands of identical, finished microchips. But even though these tiny cities are built, they are still stuck together and very fragile. They have no way to connect to a battery or a screen yet. That's where the back end comes in. This is where we test, separate, and protect the chips so they can survive in the real world. First, we test each chip to make sure it works. Then, a diamond saw or a precise laser cuts the wafer into individual squares. Each of these tiny squares is called a die, the raw heart of a microchip. We glue the working dies onto a frame and attach microscopic wires, often made of gold. These wires allow electricity to flow from the outside world into the chip. Finally, we seal that delicate chip inside a tough casing made of plastic, ceramic, or metal. This casing is the actual black square you see when you look inside a computer or a game console. This stage is what turns a fragile microscopic circuit into a durable piece of technology that's ready to be used in your devices. Before they ship out, these armored chips survive extreme temperature and electrical tests to make sure they'll perform exactly as they're supposed to. We've seen how the front end uses precision chemistry and light to print microscopic cities of switches onto silicon. And we've seen how the back end takes those cities, cuts them out, and wraps them in armor. These tiny components are what allow our phones to communicate globally, our medical equipment to save lives, and our cars to run safely. They are the invisible foundations of our daily lives.